This week we'll be modeling internal flow in ANSYS. Internal flow is flow that is constrained by some sort of external geometry. In engineering, the most common scenarios for this would be water or some other fluid flowing through a pipe, or air flowing through a duct if you're doing HVAC work. We'll also be introducing some more expanded and more complex parameters for our simulation, because the simulation this week is very true to a biological phenomena, and we want to make sure that it's as accurate as possible. So there's a lot of new parameters that we'll be introducing. The previous two simulations we did, the sphere on the left and the flat plate on the right, were both considered something called external flow, where we have a central object like the sphere, or an object that's on one side like the plate, and the external flow is considered almost infinite. This wall on the top here could go to infinity. The height of our inlet and outlet could both be infinite. And that allows the boundary layer here in the flat plate to just continue to grow over the entire distance. Theoretically, this could grow up until the point that we hit this laminar to turbulent region. In that case, then things will change a little bit. But now we're going to be talking about internal flow, and because our geometry is constrained, these boundary layers can't just continue to develop. They're going to be constrained or limited by the walls in the simulation. This is a good example of a standard internal flow that we would see. We have a fluid that's flowing in from the left into a circular pipe. We're going to assume that the velocity is constant, so we don't have to worry about the pulsatile flow like we'll deal with later on. And you can see that our boundary layer continues growing as we move along the inside of the pipe. This is the same kind of boundary layer growth that you saw with the flat plate. Unlike the flat plate, though, in our case, that boundary layer is going to grow to a certain point, and then it can't expand any further because it's going to run into its, a boundary from the opposite side of the pipe. So at that point, the boundary layer is going to not expand or contract. It's going to just stay the same. This is a bit of an aside, but in engineering, this is an important thing because this is called the entrance length. And we often, in looking at pipe flow internally, will, as a rule of thumb, say that your entrance length is generally going to be 10 times the diameter of the pipe that you're using. So you can see that now these internal flows, you have some extra constraints that have to be taken into account because those boundary layers can't just continue growing on their own. For this week, rather than dealing with the spheres and the plates that we've been dealing with, I wanted to have something that's very relevant in biology. So we're going to be looking at the carotid artery, specifically the section here where it splits or bifurcates. You can see the model that we've created on the right as it corresponds with that section on the left. We've got one inlet that comes in that will have blood flowing from the heart. Then that splits into two sections, and we've got two separate outlets. This is an important section in biology because, as you can see on the left here, where they've got this plaque, as you age, because of the geometry that is set up here, you're more likely to have a plaque build up on a specific section in this bifurcation. And the hope is by going through this simulation, you'll begin to understand why that's the case by examining the pressure and flow of blood through this area. Because we want our simulation to be as accurate as possible, we're going to be integrating a number of new techniques this week and increasing the complexity of some of the techniques we've already learned. First, we'll be doing something called local sizing. In areas of the mesh where we expect more complex flow patterns, so right at the area of the bifurcation where we know blood is going to be moving and diverting into the two branches, we'll want smaller elements in that area to better capture the trajectory of those particles. We'll also be doing something called transient flow, which is time dependent. Up until now, we've assumed that the velocity of our fluid is always going to be constant at 1 meter a second throughout the entire volume and throughout the entirety of time. That's obviously not how blood flows from the heart. So we've written a function that mimics the pulsatile flow of blood from the heart through this artery that's written in C. And I'll give you an overview of how that function works, but it's a little too high level to have you write something like that yourselves. Next, we'll be modeling the blood as a non-Newtonian fluid. You learned a little bit about this earlier. The blood is modeled using something called the Carew model, which means that the viscosity is going to be dependent on the shear rate. An example that you can see in the real world of this is if you make a slurry with cornstarch and water, the harder you hit it, so the higher the shear rate, the more solid it is, the more viscous it is. If you hit it with a hammer, it acts as like a solid surface on top. But if you just lay the hammer on top, it's going to then sink down into the fluid because that's considered a low shear rate. This particular model that we're using requires laminar flow, so we'll need to make a little modification within ANSYS to ensure we don't have any turbulent flow. And then next, we'll be doing something called particle injection, where at a specific time point in the simulation, we'll stick these little massless particles at a specific spot in the simulation, and then throughout time, we're going to watch how those particles move. And finally, we'll be doing some animation. Because our velocity fields and particles are going to be moving in time, we can't just take a screenshot of the velocity and pressure fields to get an idea of what's going on in the simulation. So we're going to take those screenshots effectively at every single time step, and then ANSYS is going to compile those into a movie for us to see over the course of the simulation. Let's take a look at the local sizing of the geometry for our simulation. On the left-hand side, you can see the exterior, and on the right-hand side, I've taken a clip so we can see the interior. And I've used something in Fluent, the meshing part of ANSYS, called a sphere of influence, where I've created a sphere around this area, and I've told it I want finer mesh elements within that sphere, roughly about half the size of the elements that are outside of it. Because as blood flows in, because these walls are relatively straight, we'll have a pretty good idea of what that blood flow is going to look like. But as soon as it gets into this region in here, where it's going to split off, we don't know for certain what this airflow or what this blood flow is going to look like as it moves through this region. We also have this expanding bulb that's on the one side. And so we want that finer mesh in this area to capture that more complex trajectories that we'll see of the particles moving through that region. Next, let's take a look at how we're going to model the transient or changing flow velocities in ANSYS. This is done with something called a UDF, or a user-defined function. These are available in ANSYS and can get incredibly complicated and complex. The manual just for user-defined functions is 500 pages. So we're going to do something that's relatively simple, but I'll try and walk you through the process here. These are going to be created for you. You'll just download it. We don't expect you to write these on your own. I first have to define pi as a number up top, because in this case, the C doesn't have a built-in constant for it. Then I define my function and give it the face here is my inlet face. That's defined in the graphical region in ANSYS, so you don't need to worry about that. But then I define a time here called t, which is going to cycle from 0 to 0.5 seconds. This allows us to get a cyclical nature that will repeat this function no matter how long we choose to run the simulation for. And we have two regions that this function will operate in. Is first, for the first 0.218 seconds, so if time is less than or equal to 0.218, we give it a velocity that's modeled with a sinusoidal wave. And then past that point, we'll just give it a constant velocity of 0.1 meters a second. If we want to graph this as velocity versus time, we'll say that this is 0.218, and this is going to be 0.1. Our velocity will look a little bit like this, and then we'll get to a point out here, say if this is 0.5, where we repeat the process again. So this gives us our pulse of velocity that's from the heart. I think our max here is probably something like 0.8, 0.7 meters a second. I'd have to get the values from the simulation. But then this will fairly accurately model what the heartbeat is doing, pushing blood through the system. As you can see, because we've got this repeating every 0.5 seconds, you should be able to calculate out what that corresponds to in a heartbeat of beats per minute. Moving on to the fluid itself, since we'll be using blood as our fluid, the model through the artery, and blood is a non-Newtonian fluid, we'll want to use a non-Newtonian model. We'll be using something called the Crew model, which is built into ANSYS, and it's given by the equation here. Let me break down these terms for you a little bit. Our mu is our viscosity. So this mu EFF stands for the effective viscosity at whatever shear rate this is. This is gamma dot, is the rate of shear that fluid is currently undergoing. We also have a couple of other terms here. We have a lambda, which is relaxation time. Which gives us an idea of how long this fluid would have to sit idle to regain extra viscosity. And then we also have a power term that comes out, this N. That allows us to create the function itself. So if we break this down, we would measure our viscosity at an infinite shear rate, and we also measure the viscosity at a 0 shear rate to then determine what our effective viscosity is at whatever current shear rate that we're looking at right now. That can be modeled in ANSYS with the models that it's got built in for Karoo. It's nice where once you put in the values for all these parameters, it will build a little graph to show you how the viscosity changes depending on different shear rates. So you can see here that as our shear rate goes up, our viscosity goes down. This in engineering is what we would call a shear thinning fluid. So the more shear that this experiences, the less viscous it becomes. If this were a pure Newtonian fluid, the graph would just be a straight line because viscosity would not be dependent on shear rate. For Newtonian fluids, the viscosity is usually a function of temperature and pressure. If you think about honey at room temperature versus honey that's warmed up, that warm honey is going to be less viscous than room temperature honey. And then one other note about this model that feels like a bit of a disclaimer you'd see on TV is that this is not valid for very small vasculatures, so in the capillaries. The Karoo model relies on the fluid being modeled as just a single fluid. When we get down into the small capillaries, we have to model the plasma as a fluid and then the red blood cells as these solids that are within the fluid. So it's something we would call multi-phase flow, but it's not something we're going to get into this semester. We'll also be doing something called particle injection on this simulation. In the past, all of our simulations have been one single time frame, so this wasn't too much of a concern. But now our simulation is going to be changing with each time step. What we do with particle injection is seed little tiny particles at the inlet here, although they can be at any arbitrary location within the simulation. And then for each time step, we calculate how much these particles are going to be moving and in what direction based upon this entire velocity field that we calculate. So then next step, time step 2, it might move around here, it might move back over here, but this is all a function of that velocity field and how it changes with each time step. The first simulations that we did where we have that single time step, theoretically a velocity particle is just going to follow the same lines all the way through here because the velocity field is not going to change with time, it's static. But because we've got this pulsatile flow coming in from the inlet, these velocity vectors are going to change quite dramatically with each time step. So we need to make sure that we're properly seeding these particles in that location so that we can track them over time. We'll also be creating a couple of different animations of the artery here. Because our simulation is going to change in time, we want our images and our video to reflect those changes over the course of that simulation. I can play here the video that I created. I think this is just 1 second of pulsatile flow, so that should be 2 pulses. And you can see just how much both the magnitude and the direction of some of the velocity vectors here changes. We'll also be doing this for looking at the wall shear stress because the different velocities of the blood flowing through here will create different stresses in the wall, and we can track that over time. Then the other animation that we're going to be doing is not in time, but in space. We can take a cross-section of the artery, say right here, a cross-section that would be mostly circular. And in time, we can move this cross-section through the different areas here. And we can take a look at, from this perspective, how the velocity changes throughout the volume of the artery. You'll notice that at this entrance region, just like with what you've learned previously with this internal flow, we would expect the highest velocity to be in the very center of this region. But that might not be the case when we get to the bifurcation with this bulb here, and as this narrows back down, it'll be interesting to look at where the highest velocity flows are in those regions. That's everything that I have as far as the background of the simulation. Now let's move over into ANSYS, import the geometry, and step through the simulation step by step. That took just about a minute. Now we've got the mesh as a green check mark, so that's all taken care of. Let me actually go back in here for a second just to give you an idea of what this looks like, if there's not too many graphical glitches on my end. Okay, that took a second, but we've got our mesh here, and I've done a few things here with the body sizing. This is our sphere of influence. You can see it still doesn't really like that. I've got our name selections already set up. So we've got 2 outlets, our inlet. The wall artery is just the walls of everything. And then the fluid domain is every single vertice or every single face here, including the inlets and outlets. So let's go ahead and close out of that and get into our setup phase. Again, we'll want double precision, and then everything else there should be fine as the options as they were before. And this will take a second to load all of our variables. Okay, so you can see we've got our model here with an inlet and 2 outlets. Looks like everything imported correctly. The first thing we want to do here on the task page in general is to change this to a transient rather than a steady solution that allows us to have the solution change over time. And then next, we'll have to do a little bit of something with the models here. So there's something called viscous turbulence, which I don't know too much about, but it means that the model that we want to use for the blood isn't going to work. So we have to first decide that this is going to be a laminar viscous model and hit OK. And then now when we go into materials, what we'll do is we'll use this as it's set up, but we'll just modify the variables that are within here. So our viscosity we can change to this Karoo. And now we've got a lot of different variables that we've got to set up. From that equation before, we've got these. Time constant is 3.313, and I'll have these separately in a document, and hopefully these will actually pop up in the video if I can get the overlays working for that. Our power law index 0.3568 and zero shear viscosity at 0.056 and infinite shear viscosity at 0.0035. Now you can see after clicking just in the window, our curve has changed, and we see that we now have a nonlinear viscosity based on the strain rate. What I want you to do is in your work, change this minimum 0, max 500, click in there. And I want you to take a screenshot of this or copy it to the clipboard, and you'll turn this in as one of the questions that we ask you on the homework, just to make sure that you've set this correctly. Hit OK. And then we still have to change our density here. Let's see, that is going to be 1,060 kilograms per cubic meter. That's the density of blood. So we're going to change this from air to blood, and we'll change and create. And we're going to overwrite the little built-in model it had for blood. Then we can go ahead and close out of that. The next thing that we want to do is to add in that user-defined function, because we're going to need to set that as a boundary condition for this inlet. So if you go up on here to the user-defined menu, and under functions, we're going to go to an interpreted function, and we should be able to browse for the location, and we'll load up that C file that we had. All the rest of these options should be okay. We can just hit interpret, and you see that we've got a lot of complex stuff that came up in the console here. This is part of this is a C compiler that it's loading up all the data from that file, the code that's within there, and compiling it into the right format. So that we can close that window and double click on our inlet. And now hopefully if we click the arrow that's next to our velocity magnitude here, we have this user-defined function profile as a inlet velocity. And we can apply that and close. So now we've got our inlet velocity. The next thing is we're going to have to take care of some of the outlet pressures, and those are going to be running at a very specific pressure. For our outlets here, let's double click on this. Rather than running at a 0 gauge pressure here, we're actually going to want to put in a value, and we're going to use 13,332 pascals. This may sound like a very weird number, but when we convert this over to millimeters of mercury, this is equivalent to 100 millimeters of mercury, where this would be an okay value for the diastolic blood pressure. That's your second number. So if your blood pressure is 100 over 80, your diastolic is 80. So we're using a diastolic of 100, which may be a little bit higher than standard, but it's perfectly within the right range for a lot of the population. So let's apply that there and apply it to the other outlet as well. And then now we've got our boundary conditions for inlet and outlet. Our walls should still remain as walls, so we don't need to worry about that one. The next thing that we'll be adding in is our particle injection. We'll do this it's a little bit of a complicated way, but we have to go into the physics section here, and we're adding something called a discrete phase. So it's a discrete phase injection, and we'll create this. We want to make sure that this is a massless particle. It can do some really cool things if we just decide to do inert particles. We can choose all sorts of different solids, liquids, and gases that have different properties, different densities for a particle that would behave with proper physics. But we're just going to go massless, so we don't have to worry about any of that. And then we're going to be injecting these at, again, some very specific coordinates that I'll try and have these popped up as well as in a document. So 0.001183, 0.006242, and negative 0.031 0.8313. These are all in terms of meters, and because this is the actual size of the carotid artery, these are really small numbers because these are offset by just millimeters. We also are going to start this at 0 and then stop at 0. That just means we're going to inject that particle once at the very beginning of the simulation and just let it move throughout. We're not going to continuously release particles from that location. So we hit OK. And then I got to create another one because we want a particle that's released at the center of the inlet here, and then one that's released on the edge. And we're going to take a look at how the velocity differs between these two particles. So again, we'll want a massless particle, and we're going 0.002758, 0.004548, oh, 0.004548, negative 0.318313. This is the same Z position because the Z face is where the inlet is. And then we can hit OK there. So now we can close our injections menu, and we'll do something now that we neglected to show you how to do for the last couple of simulations. Is in our reference values tab, we'll need to adjust some of these as well. The reference values these are the kind of the base calculations that ANSYS will use in determining some things like shear of the wall, drag and drag coefficient. So technically the drag and drag coefficient that you measured in the sphere were not scaled correctly, but they did give you still a good idea of what those values should be. So our area here is going to be the area of the surface area of this model, and it's been calculated out as 0.0013245 meters. Our density, this is our fluid density that we're using, so we're going to use the same values for blood. And then the only other thing we need to change here is the velocity reference, and that's 0.1 meters. This 0.1 meter, that's going to be what we would call our lull velocity. So after we get the pulsatile flow, that's that sine wave, it settles at 0.1 meters per second. Next, we can close that, and we're going to create a number of these report definitions, same as we had done before. You can see we've got a couple new things here because it is a transient solution. So we've got delta time, which is the change in time over the course of the simulation, number of iterations per time step, because that will be a criteria in the convergence of the simulation, and also total flow time. So let's create a new report definition, and we're first going to do a force report on drag, and we're going to do the drag force at the wall artery. So we're going to try and get the total drag force that the blood exerts on the geometry of this artery here. Hit OK. Let me also rename this. Drag force. And as a check for ourselves, we'll also want to create a report that shows us what this inlet velocity is, just to make sure we know that it's going to be varying in time and it follows the function that's been set up. So let's do a new, and this is a surface report. Let's see, where is this? This is an area weighted average, because we're going to average the velocity over the entire area of that inlet. We're looking at let's see, area weighted average of velocity there and velocity magnitude at the inlet. And we can name this inlet velocity and hit OK there. Now we've got one or two other things to do before we can start on this. We'll first initialize our setup here. We're going to use a hybrid initialization. When we used the standard initialization for the flat plate, we knew what we thought would be good, the velocity initially throughout the entire plate, so that it helped to speed up the solution to converge. Because we're dealing with a transient solution where this is going to be changing, we'll choose a hybrid initialization, and it's going to use this first time step to seed out what the velocity should be, and then it's going to recalculate that until this solution will converge. So you can hit initialize there. And we've got a pretty good residual there, 10 to the minus 8, so it's pretty well initialized. And then before we run our calculation, we actually need to go into our calculation activities, because mainly with the particle injections that we're doing, those get saved out to a separate kind of file, and we need to make sure that those actually get saved. So we'll do two things here. We'll go to, if we double click on calculation activities, hit create a solution data export. And this will also give us the opportunity to save all of the data from this simulation in some different file formats that we could use in other programs. So our file type here, I want to make sure it's this CDAT for CFD post. And then we're going to want to add in some things that get exported. So static, dynamic, and total pressure, and then all of our velocities. I'm interested in the vorticity in all directions. And then we are also interested in the wall shear stress. And I believe that that is everything that we do need. Although you could export more of these values, it just means that our report file is going to be a little bit bigger. So we want to export every one time step, and we need to make sure that we give this a location where we save it. So I'm going back to the location that I have here for my simulation, and I'm going to make a new folder called data, and I'm going to just call this Caro artery for carotid artery. Hit OK, and then this will create a file for every single time step that we're making. So we can hit OK there. And then we also want to create one of these for the particle history data. This is especially important. I think with the this other export, we don't need to do that unless we're bringing this data out into a separate program, it should automatically export into the CFD post. But just to be sure, we want to make sure it's there. So let's go to our particle history data for CFD post. We'll select both of our particle injections, and then let's see, particle variables, particle residence times. I think all of this should be fine. And then we're going to browse to the same location that we had before, this data, and we're going to name this P history for particle history, and then hit OK. So now I've got our data that's ready to be exported after we run this, and I think now we are ready to run the simulation itself. Now we can double click on Run Calculation, and our time steps here, we're going to choose 100 with a time step of 0.01 seconds. This will run through 1 full second of this pulsatile motion, and that's going to give us 2 pulses, which should give us a good idea of the flow conditions. Oftentimes when we're running simulations for research, we need to run a number of cycles for any of these cyclical quantities because of how the initialization conditions may be a little bit different from what we'd call the operating conditions, where we first have to seed what's happening inside this geometry with a couple of pulses of blood flow to get it to go into a normal routine. Max iterations per time step, we're going to go up to 200. It won't run 200 iterations per time step. It just runs until the residual decreases to a value that is okay for us. And then before I hit calculate, I want to go into the data file quantities and make sure that I add in the same thing that I did for the calculation activities here. So static, dynamic, and total pressure, velocities. We're going to go vorticity, and then shear stress in all these directions. And then at this point, I'll run the calculation. And when you run this on your own, be sure that you have allocated enough time on the CHPC. This process will probably take, I'd say, maybe 20 minutes or so because we're running so many iterations. As you may have noticed, I sped up that little process there just to make sure that you saw it going through it. But let me take a look at the residuals here, and you'll notice that we've got these sections where the residuals get really, really small and don't vary that much. And that's because our first big hump here is our first 21 steps. That's the 0.21 second. That's our sine wave, and then it settles into that constant 0.1 meter velocity. So this is all 0.1 meter velocity here, and you can see how much easier those calculations are for ANSYS to do. It went through those much faster than the other ones. And then immediately when we get to half a second, we start that sine wave again. Our residuals get bigger, and it takes a long more time to calculate the solution. Now is also an excellent time to save our project, just in case our session at the CHPC times out. And then we're done with this part of the simulation. Now we can move on to our post-processing, and we're going to create some visuals, we're going to track our particles, and we're going to take a look at making those movies. So I'll quit out of that. Now that we're back on the main screen in ANSYS, normally we'd be able to right-click on our results here and go into Edit, and it would start up CFD Post. There's a bit of a bug with that in transient solutions like we're working on right now, where it will only load up the very last time step. So what we're going to do here is I've scrolled down here past the analysis systems down into our components, and I'm going to drag in an extra results option, and now we have a separate results subprogram, and we're going to use this to analyze the results of our simulation. By default, it's not going to load up the simulation that we had because it's a separate little program. So we'll have to do that manually in loading results. We'll scroll to where you've got those data files saved. So we do need those data files that are separate from the simulation itself. We'll load up the first time step here. You can load up either of these two files. They are related. And we don't need to worry about all of the rest of these. CFD Post understands that all of these files are related to the same simulation. So if we load up the first time step, it will load up all the rest of those as well. You can hit OK on this. It might scale some quantities a little bit differently depending on what data we have displayed, but we can always manually adjust that. It does load up a little bit weird, and that's because it loads up the wireframe version of the mesh, which is just some of the edges. We can take that off by clicking wireframe, and then we'll want to enable the wall artery. So that's our actual outside mesh that we're working with. We have the majority of our data that's imported here with those case files, but we do need to import our particle tracking data separately. We do that through the import menu in the file menu, and there's an import fluid particle track files option in there. It should be in the same spot that you saved all the rest of that data, and it'll be a single XML file that will open up. You'll notice that we now have fluid particle tracking for massless particles here. Let's double click on that and modify some options. Go into the color menu and change this from constant to variable. And we're interested in looking at the velocity of this. So we'll then hit apply. And we can't see anything here at the moment because it's blocked by the outside surface of the carotid artery. So let's go ahead and modify that one as well. Double click on the wall artery, and under the render tab, we'll change the transparency to 0.7. And then we can hit apply. And you'll see we've got those two particles. One particle that gets injected pretty much in the center, and one that's offset on the side. Because when we load up these simulations, it loads up all of the steps, and the default view is at the very end. The particles have already traveled all the way through the system. So let's watch them as they actually go through. There's a cool menu up here, a little film strip. That's our animation menu. Click on this, and we're going to do a time step animation. We're going to start at step 1. Since now I've changed it to step 1, the particle tracks have gone away. And then I'm going to also save this movie. These are really nice to look at afterwards. And as it's stepping through this animation, as you're making it, it's going to be a little bit slow. But once it makes the movies, it'll run in real time. So I'm going to save this onto the same spot that I'm going to save it in my main folder that I had set up for this project. And we'll call this particle flow. And then we can hit play, and it'll play this animation. So you can see these two particles generally traveling about the same distance until they get into the one bulb. One flows completely straight through. The other one gets trapped in that little expanse. We'll let this run up to time step 100, so 2 full heartbeat cycles. If you notice the step here, we're now in that lull where it's just the constant 0.1 meter a second flow rate. Once we get up to step 50, then it pulses back up, and with that increased pulse, you can see that I think that should pop out and get pushed out of the system. It may not do it because I moved the model while I was making this animation. You should always just let it sit, but I was impatient. Okay, now it's saved that video, and you have to use the file menu here to download that to take a look at it later on. Now let's take a look at the total velocity field and how that changes over time. I'll deactivate our particle tracking because we're not interested in that at the moment. And then we can add in items up here. So I'm going to add in a vector, name this velocity. And then I want this to be in the fluid domain, which is the volume here. We'll do the entire volume, and we're looking at the velocity as a variable here. We'll use the same linear scale with the arrows, so we can hit apply. Now this should be the very end of the simulation, so we're looking at very low flows, but it can be interesting to zoom in to take a look at what the velocity is doing when you don't get the pulsatile flow from the heart. Same thing as with the particle tracking. Let's go ahead and make a movie of this. And you'll want to make sure that you're changing the name here so you're not overwriting your other one. We'll name that velocity. And then we can run through the time steps here. Obviously, at the very beginning, we get this increasing with that sine wave, that increased velocity. So we get really fast outflows up to almost a meter a second in both the interior and exterior carotid arteries. And then this relaxes down. Steps 25 through 50 here are that lull period where we're just moving at 0.1 meters a second. And then next we're going to get up to 50, so it's going to get our second pulse moving through the system. And it would be interesting to really dial in on this to see if there are any differences from that first pulse to the second pulse. We do see in some of our simulations where we have to get multiple breath cycles from the lungs of an animal to get the proper flow patterns because of the initial conditions may have not seeded the right airflow patterns at the beginning of the pulse. So it can always be good to run through a couple of these cycles. You have an error here, but I think that's probably fine. I can check to make sure that the file saved. It looks like maybe it didn't in our case. But we're not going to worry about it for now. I ran through that process again off camera, and it looks like that error I got was just a fluke. So let me show you the video that it actually creates from that process. It's just a short little clip that shows that those two pulses. This video is in real time. You can see it just ran for 2 seconds. These videos are a good way of showing off those results and seeing that what's really happening with the simulation. Oftentimes with those single time steps in the animation, everything feels like it's a much slower process. So it's nice to see these things happen in real time. Next, let's take a look at wall shear. So rather than deleting any of these things, I can just turn off the velocity vectors, and I can add a contour now. This is going to be wall shear. And our location is the wall artery. We're going to want to look at wall shear on the entire surface of this section here. I also want to change this. We'll use 101 contours to get better color variation. And rather than looking at pressure, we're going to look at just total wall shear. So give us an idea of some stresses that are on the surfaces, and I would expect that we're going to see that anywhere we get either fluid that's bumping into a certain section, so in the bifurcation here, or with higher speed, so maybe around the edges here, maybe at the inlet. Let's take a look at what that's going to look like. Okay, now this wall shear probably is just at the last time step. So same as before, let's make a video of this entire process, starting at step 1. Oh, and see, fortunately this will warn you if you're going to overwrite some of your other videos. I want to make sure to rename this to wall shear. And then let's make this new video, particularly looking at about time step 10 or 11 is going to be our max velocity flow rate with the inlet. But we can see that we do get our highest levels of shear right at the bifurcation and at the very the inlet and our outlets. With constant steady flow rates at that 0.1 meter a second, you see we get very low amounts of shear. The scale here will doesn't automatically reset, it just sets it to the highest level it sees in the entire simulation. But then now with the second pulse, we get that shear at the opening and at the exits, the bifurcation there. But we also do get a little band of wall shear where this bulb narrows down, and because that narrowing, the velocity is going to speed up through there, so that's expected to see a wall shear in that area. Okay, now that's done, that's saved. We can download that video and look at it in real time if you'd like. One of the last things that we'll want to do here is examine and try and capture something called a secondary flow. Whenever we have fluid flow through pipes that changes directions as it does through this bifurcation, we get these secondary flow patterns if we looked at it from this direction, where one direction it might run counterclockwise and then the other way it'll run clockwise. So it's these two opposing swirling flows that it's flowing in those directions as it's also flowing in this direction. So we're going to want to try and create a plane around this area to take a look at the velocity fields on those planes to try and capture those secondary flows. So let's add in a plane. Call this secondary flow. And it's going to be an XY plane. The X and the Y here are these two directions, so it will be slicing through the artery this way. If we had a YZ plane, we'd be slicing through it this way. And we probably will have to adjust this a little bit because we don't know the exact location here. But if you click on the Z here, we can move our slider back and forth. And this will update the location. I'm going to move it slightly back. Right in there. So we'll see if we can get some surfaces here. The plane, we're not going to do anything else with the plane itself. We just need that there so then we can build out the next thing, which is our streamlines. So the streamline button up here, we'll add in some streamlines that are secondary flow. Oh, and it knows that we've already used that, so this is secondary flow streamline. And rather than being a 3D streamline, which those would look at probably from the inlet all the way through, we'll do these surface streamlines. And then we can choose our secondary flow plane right here as our surface. And we'll look at velocity. Use the same plot variable here because the plot variable for velocity should be the colors that indicate the velocity in that plane. Let's apply it here and see what we get. So this indicates that we've got just normal parallel flow. This is not much of a secondary flows, but you'll remember that because the animations, we always stopped at the very last frame. So because this is a laminar setup where there's no change in flow rates, we don't get much secondary flow at that point. But let's try going through with the animation tool again. And I'll save a movie called Secondary Flow. And let's see how this changes in time. So you can see that as velocity increases, we do get these swirling counter currents that are flowing through that section. Not so much through the smaller of the two bifurcations. It could just be because we've got the majority of our blood flowing through this section. But we do still see some vortices starting to develop here. Now we're back into the constant flow area. We still have vortices that are remaining in the large bifurcation, but it is settling down, going back to that same pattern that we saw at the very beginning. And now it's going to go through that second step. We'll have to take a look at the first and second pulse side by side to see if there is any difference between the two. I feel like differences in, say, these vortice patterns are going to be more subtle than some of the other velocity fields we see. So it might be more apparent in the changes between step 1 and 2, because this is like more of a sensitive kind of parameter that we see. And I'll let that run through to the end. We now are getting back into our constant flow rate as those vortices start to calm down, or those secondary flow patterns calm down. And I get this error again, which I should just be able to run through the animation one more time, and it should save the file just fine. In addition to those animations, I'll want you to go through and find a good time step in this simulation and get a screenshot so we can take a look at those patterns. So you can do that with the Save Picture button here, and it will use that and get you this entire window. You might want to adjust some of your settings. In here, you could change how this is displayed. We can add some symbols that will also show the direction of flow. It can be a little hard to see here, but we do have arrows going down here. Let's go 3D arrows and see if we can get those. Yeah, so now we do see direction of flow, and the size of this arrow is the magnitude as well. So it can be good to take a look at that. Play around with these to get something good that really visualizes the secondary flow patterns during the pulsatile flow.